Math 110, Logarithmic Functions and Graphs, Sections 5.3. Now, if you notice from our past lesson, we examined exponential functions. And when we looked at those exponential functions, we noticed that they were one-to-one. Now, to do kind of like a brief picture of that, if I wanted to sketch that here, that's kind of like what an exponential function looks like. It passes that horizontal line test. So because of that, there has to be an inverse. So let's look at one of those functions, f of x equals 2 to the x power. If I replace my f of x with y, I get y equals 2 to the x. Then I swap my x and y's. Okay, so all I'm doing is just trying to find the inverse. Now this is where we get the interesting statement. Because what my y equals, if I were to get y by itself, y is the power to which I raise 2 to get x. Okay, so I'll say that phrasing is this y, it's that power that I'm raising 2 to give me x. That's what my y is. And so replacing that y with my function notation, I could say that my inverse is the power to which I'm raising 2 to get x. Now, it's kind of annoying, a little tedious to say the power to which I raise 2 to get x, so we use that symbolically to represent as log. So in this case, log base 2 of x is essentially saying the power to which I raise 2 to get x. So because of this, I can basically say that logs and exponents, they're going to be inverses of each other. So kind of going further with that logic, if I know that my f of x is 2 to the x power, therefore my inverse is log base 2 of x. So therefore, if I plug in 8 into my inverse, that's going to be log base 2 of 8. It's going to equal 3. And the reason being is because 3 is the power to which I have to raise 2 to get 8. I can do the same thing with, if I did f inverse of 27. That's going to be 3 as well, because 3 is the power to which I have to raise 3 to get 27. Now, we don't have to get caught up with this logic because it's kind of self-explanatory once we start manipulating with logs, but that's essentially the phrasing or what a log means. And so we can make this statement, f of x equals a to the x, given by that our f inverse is going to be log base a of x. So here's some visuals of what's going on. Here's our 2 to the x. There's our f inverse, which is a log base 2 of x. Notice how it crosses that line y equals x. Because it's a reflection over that line, it kind of symbolically shows that these are going to be inverses. Here's 1/2 to the x power. This is a log base 1/2 of x. Once again, they have that reflection over that line y equals x. Now, when we're able to manipulate these, one thing that's going to help us is being able to simplify basic logarithms. And what we're going to be doing if we're trying to simplify or evaluate is we want to manipulate our logarithm to where this statement is going to reduce. Log base a of a to the b power equals b. The log base and the base are going to cancel out when they're the same. So if I had log base 10 of 10,000, I have to somehow manipulate this 10,000 to where it's going to be the same as that base there. And so I can say log base 10 of 10 to the 4th power. Now this log base 10 and this 10 are going to cancel out. And so I'm left with 4. And that's going to be the result. If I had log base 10 of 0.01, well, that 0.01 is the same as 1 over 100, which is the same as 1 over 10 squared, which is the same as 10 to the negative 2. So I can replace that 0.01 with 10 to the negative 2. Now that log base 10 and the 10 are going to cancel out, and I'm left with negative 2. Log base 3 of 27. I can change the 27 to the 3 to the 3rd power, and so the log base 3 and the 3 will cancel out, and so I'm left with 3. if I had log base 9 of 3, this is where it gets a little bit more abstract because somehow I have to make that 3 to where it's going to be that 9. And so doing so, you should kind of like think about, well, maybe is there any roots that evolve with that? And so I know that 3 is the same as the square root of 9, and I can rewrite 9 as, the square root of 9 as 9 to the 1/2 power. And so now the log base 9 and the 9 will cancel out, and so I'm going to be left with 1/2. Log base 6 of 1. 1 is the same as 6 to the 0 power, so I get log base 6 of 6 to the 0 power. The log base 6 and the 6 will cancel out, and so I get 0. Log base 4 of 4, it's the same as 4 to the 1st power, so the log base 4 and the base 4 cancel out, and so I'm left with 1. Now these are going to be fundamental identities. Log base a of 1 is always 0, and log base a of a is always 1 for any log base a. So for any base, log base a of 1 equals 0, and log base a of a equals 1. Now we're going to be converting between exponential and logarithmic equations. So if I have 16 equals 2 to the x, this is an exponential equation because it's an exponential form. 2 to the x power, that's an exponential form. So to convert it into a log equation, what I'm going to do is I'm going to perform the inverse of this base here. And so the inverse of it is going to be log base 2. Since that says base 2, the inverse is going to be log base 2. Now I wrote it like below here. It's actually supposed to kind of like go behind it right there. And so what's actually going to end up happening is this log base 2 and that 2 are going to cancel out, and I'm going to be left with log base 2 of 16 equals x. This right here is going to be my logarithmic equation because there's a log in it. If I had 10 to the negative third equals 0.001, so this is an exponential form right now. I need to get rid of that base 10, so I can take log base 10 to both sides, which is the inverse. So rewriting it, because I want to write it there, but it's kind of hard to squeeze it in. The log base 10 and the 10 are going to cancel out, and so I'm going to get negative 3 equals log base 10 of 0.001. And that is my logarithmic equation. For c, we're going to be introducing e now, and we're going to define it a little bit more later. But what cancels out with e is going to be log base e, and so those are going to cancel out there, and so I get t equals log base e of 70. Now example number 4, we're going to be converting to an exponential equation. So right now it's log base 2 of 32 equals 5. I want to convert that log into an exponential form, and so once again we perform the inverse. Now the inverse of log base 2 is going to be base 2. And so I get 2 to the log base 2 32 power. The 2 and the log base 2 are going to cancel out, and so I get 32 equals 2 to the 5th power. For b here, I have log base a of q equals 8. So to get rid of this log base a, I have to take base a to both sides. It's kind of like I'm turning this into now the new exponent. And so I have a log base a of q equals a to the 8th. Now these are going to cancel out, and so I'm left with q equals a to the 8th. And this last one here, x equals log base t of m. So to get rid of that log base t, take base t to both sides, and so you get t to the x equals t to the log base t of m. That t and that log base t are going to cancel out, and so I get t to the x equals m. The next thing we're going to be talking about is the change of base formula. Now sometimes you're not going to be able to simplify a log like we did in like the very first few slides, where I was able to take like log base 2 of 16 and how I manipulated the 16 to where it had base 2 and things canceled out. Sometimes we're not going to be able to do that. So like this first one here, this log, which is going to be base 10, log base 10 is the same as log. That base 10, there's no way I can manipulate that 256 to where I have a base 10. So we need to use the change of base formula to do that. Now because this is in base 10 and base 10 is in our calculator, I can just enter that straight into my calculator. enter log 256, boom, there's my answer. But log base 5 isn't in my calculator. And so I'm going to use this formula here, log base a of b equals log b over log a. So I'm going to enter into my calculator log 24 divided by log 5. And so into that calculator I get 1.974. And my next one, log base 2 is 61. So log b over log a, so log 61 over log 2. And so entering that in my calculator, I get 5.9307. Another thing we're going to define right now is log base e, which we kind of mentioned in one of our slides previously. That is the same as ln, and we define that as natural log. And so instead of writing log base e, I'm now going to write it as natural log. Now, they still have the same properties. So since log base e, and it's the same as ln, this is technically log base e of e, those are going to cancel out and I'm going to get 1. The other element to this is ln exists in your calculator. So I can just enter ln of 27 in my calculator and I'm going to get 3.296. If I enter the ln of 2.7533 in my calculator, I'm going to get 1.0128. Now these properties still apply because remember this is log base e, so ln of 1 is still 0 and ln of e is always going to be 1. Now instead of using the change of base formula where I said log b over log a, because this change of base formula is just creating ratios of logs, technically this is the same ratio. So if you had wanted to, you can do ln of b over ln of a instead of log b over log a, and you're going to get the same answer. Now when graphing, these are going to be the different properties of logs. So we're going to have log base a of x, where a is greater than 1. When a is going to be less than 1, it starts creating reflections, but that's not something we're going to discuss in this class. They're all going to be continuous, as you can kind of visualize here. They're all 1 to 1, so it passes that horizontal line test. The domain naturally is from 0 to infinity, okay, because we have this vertical asymptote here at 0. My range is from negative infinity and it goes all the way up to positive infinity. It's always increasing. I have that vertical asymptote at x equals 0. The starting point that I'm going to be using is going to be 1, 0. That's my x-intercept. There is no y-intercept, so it naturally never crosses the y-axis. And this is going to be my standard form equation, log base a of x minus h plus k, where h is still your horizontal shift and your k is going to be your vertical shift. So if I wanted to graph my log, there's 2 ways to look at it. One of those ways, I could take 1, plug it in, log base 5 of 1 is always 0. Take 5, plug it in, log base 5 of 5, since that's 5 to the first power, that's going to simplify and I get 1. Log base 5 of 1/2, or 1 over 5, well, I can manipulate that 1 over 5 to 5 to the negative 1. The log base 5 and the 5 will cancel out, so I get negative 1. And I can do the same thing with the 25, and that's how I get, or 1 over 25, and that's how I get negative 2. So know that you can pick nice values if you wanted to, and you're going to be able to graph nice values. The other alternative is I can say log base 5 of 3. Well, I'm going to have to use my change of base formula. Log base 5 of 4, use your change of base formula. And so you're going to get those values, and once you do, you can plot them on your graph. So 1, 0, the other one's 5, 1, okay, 1/5, negative 1, right? That's about right there. So just know that you're able to use either nice values to do it or not nice values. Same thing here, ln. So there's no exact way to simplify it, so you just want to enter those values straight into there, ln of 0.5, ln of 1, ln of 2, ln of 3. And so when you do that, you're going to get this image here as your graph. See, it's still crossing at 1, 0. Now, if I wanted to describe what's happening with my function, because we said this is a horizontal shift, right? So if I have ln of x plus 3, I'm going to have a horizontal shift, and it's going to shift in the negative direction, 3. So I have a horizontal shift of negative 3. And that's it. My next one, If I had ln of x minus 5 plus 2, here I have a horizontal shift of positive 5, and I have a vertical shift of up 2. Now when we find the domain of logarithms, it's normally 0 to positive infinity. Now another way of thinking about it is that x is going to be greater than 0. So when I find the domain, all I need to do is take whatever's inside the parentheses and set it greater than 0. So no matter what I have written here, what I can do is I can say x plus 5 is going to be greater than 0. And then I can subtract 5 on both sides, and so I get x is greater than negative 5. And so creating that in interval notation, parentheses, because there's no equal to, it's going to be negative 5, and it's going to go all the way to positive infinity. On this one, I take what's inside the parentheses and set it greater than 0. Solving for x, so I add 2 to both sides, I get negative x is greater than 2. Then dividing by negative 1, I get x is less than negative 2. And so my domain is going to be from negative infinity all the way to negative 2.